Hello, welcome to session number 4 in the playlist System Design. My name is Anurag Nigam. So, what we're going to do here is we are going to look at the RF portion of SystemVue, which is Spectrasys. And here, let me tell you, there are two analyses which are available for RF. One is the linear analysis for passives, and that is also used for small signal characterization. The other one is the RF system analysis. So first we are going to look at the linear analysis, and for that we can pick up any passives. So for example here, I have just saved this project as example RF, and then this is the design here. So I can rename the design here. Let's rename this as BPF Characteristics. Okay, so BPF Characteristics, and I am going to pick up a band pass filter. So here is a band pass filter. So there is Butterworth, Chebyshev, elliptic, and then Bessel. So I'm going to pick up let's say elliptic filter, because elliptic filter is going to have sharp cutoffs, and I'm going to use this as an image reject filter. So I place that filter here. Now if you look at its characteristics, you can specify here. So this is your insertion loss, let's say 0.1 dB, and order of the filter is 5. Now when you go ahead and design this kind of filter, I have covered this in another playlist, microwave and millimeter wave circuits using ADS, so you can refer to that playlist. But here it's a behavioral level model, or it's a equation based model. So all these things would make sense if you refer to that playlist. Here the stop band attenuation I'm looking at is 60 dB, and I have to set the frequency. So for 5G we are in 3.4 to 3.6 gigahertz band. So let's put here gigahertz, let's put here 3.6 gigahertz, right? And then Amax is 100, and we are all set. So basically these are the characteristics of a band pass filter. Now for doing the S parameter simulation or linear analysis, we need ports. So we need input ports. So input ports in this case are pins. Now pins can also be used as a signal source, right? And they change their roles. So basically they act as signal source on this design level, but as soon as you take it to a higher level and insert it down in the hierarchy as a component, then these pins start acting as your 50 ohm ports. So there are two functions of these pins. So let's look at the output pin or output port here, and let's connect it. So the schematic basically is complete. Now what I have done is, when you start a workspace, this comes with the data flow analysis here, which I have just deleted, right? I'm going to add my own analysis here, and that's a linear analysis. I'll call this as sim BPF, right? And then it's pointing to that BPF characteristic schematic, and here the unit of frequency I'm going to put as gigahertz, and I'm going to go from 3.4 gigahertz to 3.6. Rather, I will go from 2.8 gigahertz, because I want to look at both pass band, stop band characteristics. So I'll go from 2.8 gigahertz to 3.8 gigahertz, and I want 501 points, right? And we are all set, and click OK, and the simulation is done. We can add a graph. So I'll add a graph here, and here under general, this is post processing, by the way, you have S to 1 here. So basically here it's by default going to be dB magnitude, right? So but if you want, you can click this one and just say OK, and then look at its characteristics. So basically that's your elliptic filter characteristics from 3.4 to 3.6 gigahertz, and here you would have a 0.1 dB ripple, which you can't see here, but that's what it is. Rather, I'll put from 3.3 to 3.2 gigahertz, for 3 to 4.2 gigahertz. So let me just change this a little so that this thing is centered. Okay, so for that I'll just go here and I want to simulate from 3 to 4.2 gigahertz. Okay, and simulate, and here axis has to be auto, so kind of you can center it out. So this is your band, and this can be used as an image reject filter, and everywhere I'm going to be better than 60 dB, right? And the max value you can see is 100 here. So elliptic filter has got ripple in stop pass band as well as stop band. Now this filter has sharp cutoff edges, and the issue here is the group velocity, which is basically d theta by df, right? Or yeah, so that group velocity is going to be peaking on the edges, right? So that is important in case of filters, but I'm going to use this as an elliptic filter, right? So we have elliptic filter, so we know how to do S parameter simulation. Now I can also look at another graph here, so of course I can just add here. So this is the BPF characteristics, BPF char, so that is the name, and I can add a title P image reject filter characteristics. Okay, so we are all set. Okay, so we cannot just name them same, so let's find. Okay, so this is there, and you can look at its return losses also. You can add here S11, and again that magnitude can be dB, and you can also add here S22, and this is a symmetric network, so they are going to be alike, and say okay. So that's the characteristics, right? So the return loss is better than 13 here across the band, right? So fine. Okay, and by the way, you can see this fifth order, so you'll see 5 poles here, 1, 2, 3, 4, and 5. Okay, so this is the characteristics of image reject filter. Another thing you can do is you can go here and plot this return loss in a Smith chart. So you go to general, and let's look at S11 and S22, and this is going to be the entire thing, and say okay. And over here you can go here and change this to Smith chart and say okay. So basically this is the reflection characteristics of the filter, right? So you are looking at in Smith chart here, and here looking at in the rectangular plot, right? So there's no phase information here. There's all the phase information plus magnitude information is over here. Okay, so we are all set here with the S parameter analysis or linear analysis. Now let's look at some other examples. So we can close this. I can make a new design here, and I would name this as signal source, okay, and say okay. And in this signal source I'm going to put here a signal source here. So there is a multi-source here, which basically acts as, it can be configured as any source if you want. So this one, okay, if you double click it right now, there is no source here added, right? And here what you have to do is add a source. So when you add a source, it says description, it's a CW source, and its level is -50 dBm, right? Okay, so this is just a single frequency source, right? Then you can specify, wideband source and specify the bandwidth. You can specify frequency spectrum and stuff like that. You can put modulated source here. For now I'm going to put a CW source. Now another thing is, when you characterize something like a PLL, you can put here phase noise information. So basically what you see here is in megahertz, so basically 1e minus 3, that is going to be 1 kilohertz, okay, and so on. So 1 kilohertz, 10 kilohertz, 100 kilohertz, 1 megahertz. So these are the offset numbers here, and all at that offset you have a phase noise specified. So now if you want clarity on this, there are other playlists where I talk about PLL phase noise or VCO phase noise, which you can characterize there. So I'm going to not put any phase noise here, that's fine. So it's 100 megahertz and minus 50 dBm is the power level, and there is a phase information which you can put here. In case of multiple tones, you can put different phases here, and you click OK. You don't do anything, so that source is added. So that S1 source is added here. You can edit it. You can say that this is a CW source. Okay, so that's there, and say OK. Now if I want to have a look at it, okay, all I have to do is I have to put here an output pin, right? And you can just put that over here, and let's connect it here like this, right? So this is done, and I am going to specify analysis, which I'm going to call here RF system analysis. And in this I have to specify the design, which is signal source, and I have to specify the data set, where I would say I'm looking at pure tone. So that's the data set name, it doesn't matter. And here the channel bandwidth is 1 megahertz. So this channel bandwidth is basically for the noise computation, right? So I'll just show you what that is in a second. And it says that, okay, the summary of the schematic on which it is applied, there is only one source here which has these characteristics, and say OK. So once you do that, right, and you click this, you have a second data set which is generated, which is pure tone, right? Now you can look at it by double clicking at it, and you can look at, let's say, DC independent. You can look at the power level, or this is the voltage level. Okay, so let's plot the output. Okay, so you can just right click on this pin and say add new graph and table, and it says new power plot at node 1. So I'm going to plot the power level. Okay, so now here I see I have 100 megahertz minus 50 dBm, but then I see the noise at any point is minus 114 roughly. Now why minus 114? This is because your bandwidth is 1 megahertz, right? So you are integrating the noise power over 1 megahertz, and that means that is 10 raised to minus 1 megahertz is 10 raised to 6. So in case of the noise, it will be in dB, it will be 10 log 10 of 10 raised to 6, which will be 60. So if the noise floor is minus 174, then you add 60 to it. So minus 174 plus 60, that's going to be minus 114. Okay, so basically this channel bandwidth which you specify in the analysis here, right, this channel bandwidth is that. So you are integrating noise over 1 megahertz channel. Now if I put this as 1 hertz, for example, which will be 1e minus 6, right? So that will be 1 hertz, and if I run this simulation, okay, so now you see the power has come down to, noise power has come down to minus 174, right? So now the noise is integrated over 1 hertz, right? So that will be the noise floor minus 174 dBm, right? So you know the reason why we are putting here the bandwidth. This bandwidth basically is the bandwidth for the system over which the noise is going to be integrated. Now in our case, right, we are looking at 3.4 to 3.6 gigahertz, right? So we are looking at that kind of thing. So in that case it will be 200 megahertz here, right? So that is your total system bandwidth. So you may be integrating noise over the entire system bandwidth. Okay, or in this case if I was to put the channels and then look at that, because I will have filtering once the down conversion takes place. So in that case the channel bandwidth would be put here rather than the system bandwidth. Okay, so this is for the noise integration, right? Okay. Okay, so this, I think this graph you have understood. This graph is just showing a CW source. Okay, so now this is very simple. Now let's go ahead and do something more complex. Okay, so let's say I have this input at 100 megahertz, right? And I am going to upconvert it. So I am going to upconvert this to my carrier frequency. So for that I would need some form of a mixer. So that's a mixer here. Sorry, it should not be connected here. Let me. Okay, so let's look at this mixer. So what we do here is we model a mixer, right? And you should know that there is no across frequency response here. This is more to do with across power, right? So I can say my conversion gain typically of a Gilbert cell is around 10 dB or 12 dB gain. Then am I looking at the sideband suppression? So basically if I mix 100 with 3.5, so that will be 3.6 and 3.4. You'll get both, right? If you do that. So first of all, let me just cancel this. Let's go here to because we are looking in this band, let's put here an IF frequency. So let me just add this, and let me just edit this to 11 megahertz. Okay, so that's basically the channel bandwidth. Okay, so that's fine. Okay, so if I take 11 megahertz, right, so here it is 10 dB conversion gain. I'm looking at up conversion, so I'll look at sum, and the LO frequency in this case is, I can specify the LO frequency here, or I can put the LO frequency through one of the terminals here, right? I can put the LO frequency from here, and so I'm going to just leave it blank. Noise figure here, let's say, is 5.4. okay, and let's see what else I can do. Okay, now this is called, the linearity. This is how you specify the linearity. So for this I'll have to explain you what you are specifying here. So let me put you on a pause. Okay, back again. So let me just show you what I mean by linearity here. Okay, let's go to a new page. So what happens is the following. So let's say this is my P in and this is my P out. So when I put in, I increase the input power, the output power increases linearly to a certain point, and after that it basically, right, or in terms of gain, this will go flat. And so what's happening here is you can represent P out is equal to G0 times of P in this region, right? P out is G0 times of P in, so this is a linear response. Now when you reach in this region and compression starts, then this relationship is no longer linear, and to approximate that you would have a higher order equation here, G0 times of P in plus G1 times of P in square plus G2 times of P in cube plus and so on, right? So whenever you run into these squares and cubes to model this transfer characteristics, you run into something called mixing, right? So what is mixing is the following. If I take two signals A and B and add them, so these are two tones now, so I can say A is equal to A0 cos of omega 1 t, and B is A1 cos of omega 2 t, right? So when I take these two this as P in, so this is a two-tone input, right? And if I subject this to the square nature of this characteristics, then this will become A plus B square, which will be A square plus B square plus twice of AB. And if I insert these values back into this, I would be getting A0 cos square omega 1 t, right? Plus A1 cos square omega 2 t, right? Plus you're going to have twice of A0 A1 cos of omega 1 t into cos of omega 2 t, right? So what that would mean is I can represent this as twice the angle, so this will become A0 by 2 plus 1 cos square theta is 1 plus cos 2 theta, right? So A0 cos of twice of omega 1 t by 2, and similarly I will have A1 by 2 plus A1 by 2 cos twice of omega 2 t. So now you see, because of these two terms here, you have generated second harmonic here, right? And then you have also generated DC components. Okay, besides that, if I was to analyze this one, cos of A into cos of B, okay, cos of A plus B by 2 plus cos of A minus B by 2, right? So I will have A0 cos of A into cos of B, cos of A plus B by 2, cos of A plus B by 2, right? Cos A plus cos B. Okay, and then you'll have just 1 second, cos of so that would go away, and then you'll have cos of A minus B by 2. Okay, so you have generated again something close to second. So let's say if omega 1 was approximately equal to omega 2, so then what you have generated here, you have generated anything close to second harmonic, and here you have generated anything close to DC, right? Omega 1 minus omega 2, if they are approximately equal, then this term will be DC. So what you are seeing is that the even order mixing results in components which are at even harmonics or at DC, so they are kind of far away from
your frequency of interest. So for example, if I take omega 1 and omega 2, two close by frequencies, then I'm generating components at twice of omega 1, twice of omega 2, and then somewhere here omega 1 plus omega 2, right? And then at the DC level I have got DC, and then close to this would be something like omega 1 minus omega 2, right? So this basically is what is happening. Sorry about that. This is what is happening across frequency band, right? So even order mixing results in components which are far away from our desired bands. Now, if I was to look at the third order mixing, which comes from here, cube term, so this is the closest one. So then what is going to happen? We are going to have a plus b cube, which is going to be a cube plus b cube plus thrice of a square b plus thrice of ab square, right? So in this case, let me not write all the trigonometric formulas. I will just know that this will result in thrice of omega 1. This will result in thrice of omega 2. This will result in thrice of omega 1 plus omega 2, sorry, twice of omega 1 plus omega 2 and twice of omega 1 minus omega 2, and this one would result in twice of omega 2 plus omega 1 and twice of omega 2 minus omega 1, correct? So now this is the third harmonic, close to third harmonic. This is close to third harmonic. This is third harmonic. There is no DC generated here, right? But you have, if you look at the picture, you will have omega 1, you will have omega 2, then you will have here twice of omega 2 minus omega 1, and you will have here twice of omega 1 minus omega 2. Right? So these components are close to your desired band. And if I consider a multitone case, then this basically would look like this, and then you have got the third order components over here, right? And if I take a complete spectrum, then the spectrum is going to look like this, right? So these components are coming in this case because of the third order mixing, and I'm considering two-tone case here and a multi-tone case here, and only third order mixing is considered. Okay, now what will happen with the fifth order mixing? Fifth order mixing will also result in components which are going to be over here, right? All odd order mixing will result in components like this. Now let's say that there was another channel sitting here, just adjacent to this, there was another channel here, right? So if this would have its own intermod components like this, right? So in this case, its spectrum would be like this. Okay, so now this is channel 1 and this is channel 2. Now the channel 2 results in some components which are lying in channel 1, and channel 1 results in some components which is lying in channel 2, right? Which is lying over here, right? So now you would have understood what non-linearity will do. Non-linearity will result in components which are going to be in the adjacent channel, and then this ratio of main channel to the adjacent channel, this would be known as ACPR, right? So this basically is known as spectral regrowth, right? So this is known as spectral regrowth. What it means, it is going to be one channel spilling energy into the adjacent channel, or it may be also spilling energy into alternate channel. right? So for example, I can say that my channel may result in something like this. Okay, so this is the adjacent channel and this is the alternate channel. So the adjacent channel is going to be affected. Okay, so adjacent channel is going to be affected. So in this case, it's like this, and like this, and like this, and then like this. So this component is the adjacent channel component, and this component is the alternate channel component. So it can not only affect the channel which is adjacent, but it can affect multiple channels which are, far away. So this is known as spectral regrowth. This is because of the non-linearity. And one more thing I want to mention is the channel bandwidths, and then there is no guard band, for example, or if there is a guard band, then that's helpful, right? So if there is no guard band, then this is a severe case, right? And it's purely dependent on the linearity. There's no way you can filter this out, because you will require the filter to be a parametric, and you want the filter to be shifting channel by channel, and you would be you would like to have a very sharp cutoffs. So basically what it means is that you will not be able to get it through filtering. The only way to improve this situation would be to minimize this non-linearity. That means to operate the system backed off. So if this is the compression, then you operate the system somewhere over here, and this would be called the back off, right? So you are operating where this component is dominant, while this non-linearity components do not exist. So that's why we back off, right? Now let's see this in terms of two-tone. Okay, this is a multi-tone case, so this is a continuous spectrum. In two-tone, these are called IP3 or IM3 components, right? And if you look at this factor 3, okay, if you look at this factor, well, not even this factor, I would say not this factor, but these are the cube components, right? So basically, look at here. So this is a cube component, right? So if I express this in logarithmic, right? So it's say 10 log 10. So if I'm going in dBm, then 10 log 10 would be multiplied by 3, because this is in power of 3, right? So it will be 3 times. So the gain offered here would be 3 times the linear gain here. Basically not exactly like that, but once you are in the nonlinear region, what it is saying is that the IM components are going to grow much faster with power than the linear components. And what that would mean? That would mean the following. So if I have this and I have the linear component, so basically let's say this is growing like this, and as soon as I go into non-linearity, which is let's say over here, so the IM components, IM3 components are going to grow, and the IM3 growing components are going to grow faster. So basically this slope is 3 times of this linear slope. So let's say this is the linear slope here, and this is your 3 times the slope over here. So they are going to meet somewhere, right? So at this point, the output power here at this point is going to be called output IP3, and this would be called the input IP3. Okay, so what it means is at this point the magnitude of these components will come equal to the magnitudes of the desired components. So that's how you define it. At this point, the magnitude of the IP3 components or IM3 components is going to be the same as the magnitude of the linear components. Now here, beyond this, you will not have a significant desired component, so it will be useless for you. So this will be the upper limit to which you can use it. So basically I have some things which I have to tell you here, some numbers here. So let's say this is the gain, this is flat over here, and as soon as you go into nonlinear region, this is called compression. So let's say this is gain here, and by the time it compresses by 3 dB or 1 dB for example, so the gain drops by minus 1 dB. So that is known as P1 dB. Okay, so P1 dB is one measure of non-linearity. Then this basically saturates out, the power saturates out from here. So this is called P sat. Okay, and this usually happens in 3 to 5 dB range. Okay, so what it means is that let's say you have a P1 dB of let's say 28, then 3 to 5 dB above that you are going to saturate. So worst cases or the best case can be 5 dB. So 28 plus 5, 33. So P sat would be roughly 33 if P1 dB is let's say 28. So it will be in that range your P sat would be compared to P1 dB. Now what is the relationship between P1 dB, which is at this point, and TOI here, right? So this is also, by, you can prove it, but usually it is around 10 to 12 dB. So if I say my P1 dB is 28, then my OIP3 is going to be 28 plus 10 or 12, right? So let's say 12. So it will be 40. Okay, so this will be at 40 dB. And then there's one more thing which is called the SOI, or the second order mixing components. Of course, the second order mixing components has got a square in it, right? It has got a square in it, means that the rate with which these components will grow, the second order components, would be much slower, right? So they are going to go at twice the rate, right? So they are going to meet much further compared to TOI, right? They are going to meet much further here. So that will be called SOI, and SOI is another 10 dB above that. So in this case, I can say OIP2 would be equal to 10 dB above that, so it will be around 50 dB. Right, so you got an idea of how do I specify non-linearity, right? Now this can take place in case of a mixer also, in terms of conversion gain, or it can take place in terms of gain in case of an amplifier, right? So with this background, let's go back to what the mixer specifications are, right? So just one second. Okay. Okay, so here we know what these numbers are. Now I'm not going to put in allo here, I'm going to put in allo separately, and I'll explain you some more things related to this. Now here P1 dB, okay, is the 1 dB compression, right? So let's say my input power is minus 50 dBm. Now how do you get this number minus 50 dBm? Actually this is the output of a DAC, right? So the DAC output may be in microvolts or something like that. So that number comes from there. Now let's say that this has a gain of 10 dB, right? So that means that once you put here minus 50, right, so you are going to get minus 40 at the output of the mixer. Now when you specify linearity, you would say that where does the gain become minus 9 rather than where does the gain become 9 rather than 10, right? You have to specify that power where the gain will drop by 1 dB, right? So let's say that this does that at minus 30, right? So you can push the input to the mixer up to minus 40, at that point minus 41, at that point the output is going to be minus 30. So it is compressed by 1 dB, right? And you can also specify the saturation, which will be 5 dB above that, so that will be minus 34, let's say, dBm, right? And then your IP3 in this case for this mixer would be 12 dBs above the 1 dB, so this will be around 2018, so it will be around minus 18, right? And then IP2 will be another 10 above that, right? So it will be at minus 8. So this is how you specify the entire compression characteristic. So this is a forward path. What about the isolation, right? So there should be something called isolation here. Let's see, lower harmonics, show more frequency, show more parameters. Yes. So this is your isolation. I think this is the LO to RF isolation. Okay, so LO to RF means the LO frequency leaks into RF, right? So that is set as 30 dB, LO to RF isolation. LO to IF isolation, which is the output of the mixer, that's another 30 dB. And then this is the reverse isolation, which is around 300, which is input reverse isolation, out to in reverse isolation, and this is out to LO reverse isolation. So out to in reverse isolation, okay, is basically the one which is really called a reverse isolation. And that reverse isolation, so let's say the gain is 10, usually it is going to be minus 10 means that you are going to feed back the entire signal back. Okay, so if the forward gain is 10 and minus 10 is the isolation, that means whatever is going forward, it is coming back in reverse isolation at the same power level, right? So that will be the recipe for oscillations. So it should be 20 dB at least better than that. So basically I can specify here something like minus 30 is a good reverse isolation because the gain is 10, right? And here this is a LO to reverse isolation, out to LO. So out to LO means I to L. So basically whatever IF power, how much is leaking into the LO path. So this is a very large number here. Now LO to RF isolation. This is RF to IF isolation. LO to RF isolation, right? This is the one which is important here. Now, because RF and LO are far apart in upconversion, okay, so RF is around 11 megahertz here, and LO is around 3.5 gigahertz, so it's far apart. So that isolation is going to be good, right? On the receiver side, this isolation is going to be bad because RF would be separated from LO by 11 megahertz, right? So when it comes to direct conversion, it becomes much worse because in that case, RF and LO are same frequencies, right? So you understand what that number is, right? So you can put here a large number here, right? Because the frequencies are differing a lot, right? You can put here 40-50 dB isolation here, okay? Now LO to IF isolation, so basically this is called a feed through. LO feed through to the output, and these two frequencies are almost similar here now, because this is 11 and this is 3.5 for example, then this will be 11 megahertz plus 3.5 gigahertz, so that will be close by, right? So then the feed through would not be as good isolation. Now usually this is good because of the balanced nature of the Gilbert cell. So I'm not going to go into discuss circuit components, but whenever you put something on the system level, it has to do something with the circuit level also, right? So if I put here, okay, I have this, and it says LO is 7 dBm. Well, I don't care about that. I'm going to put in here my own local oscillator and do things like that. Okay, so can I shift the text up? Okay, so here I take this and I upconvert this, but then I have here the suppression specified, right? So I'm saying I'm interested in the sum frequency, not the difference frequency, right? So let's see if there is a parameter for that also. Sideband suppression. So I don't see that. I don't see sideband suppression. Maybe it will just completely ignore this difference component. Usually what happens is you get both of them equally. So for example, if I take something which has a bandwidth of, so let's say that this is the baseband. Okay, so I have this information up to 11 megahertz, let's say 11 megahertz. Okay, so when I upconvert it, okay, so I am going to get the plus side, and I'm also going to get the minus side, and there is no way you can suppress this out. So usually you are going to have one band, we are going to transmit both sides, right? So this will be at 3.5 gigahertz. So there is no way we are going to distinguish between the two in upconversion. The both sides would be there, right? It cannot be SSB single sideband kind of thing, because there's no way you can filter out the other components. There's no way you can suppress them, right? So you'll get both of them. So if this is 11 megahertz bandwidth, then you are going to get 3.5 plus 11 megahertz and 3.5 gigahertz minus 11 megahertz. So this is going to be symmetric. Now, when you do direct conversion, you are going to mix this with 3.5, and that means that once you mix this 3.5 with this, then you are going to get this spectrum back, but then over this it will fold, the same spectrum on the negative side will fold over here, right? So this is a direct conversion, what it does, right? And if you have an IF frequency, then basically this would be offset. Okay, so this will basically move out, so the negative side of the spectrum will not fold over the positive side if it is going to be an IF frequency, right? Okay, so unless you do come back to the baseband, and eventually in the heterodyne you will come back to the baseband, in that case again it will fold up, the negative side will fold over the positive side. Okay, so I hope you understand what we are doing here. So let me tell you, there's no way to filter this. Of course I'm looking at sum. Another thing is over here, this is upconversion. You do not have any filtering over here, because you cannot put channel filters here, right? So nothing over here. This will directly go into the gain stage here, which is going to be a PA or first or second gain stages, something like that. If you put gain over here, that will be more like your baseband gain, or in case of heterodyne it will be IF gain here, and in that case you can put filters around it. But once you have done the conversion, upconversion, you won't have, because the frequencies are close by, right? So here, let's see if I have an oscillator. So there is an oscillator here, and here we specify the frequency of oscillation, right? Okay, so the frequency of oscillation here is going to be 3.5 gigahertz, right? So you're taking baseband and doing a direct conversion, up conversion to 3.5 gigahertz, right? And then you are going to specify, so this is probably the phase noise, right? Frequency offset, and then the phase. Where is the phase? So this is the phase noise. right? So this combination, this and this. So you are specifying phase noise at 1 kilohertz, 10 kilohertz offset, 100 kilohertz offset, 1 megahertz offset, and then these numbers are minus 70, minus 90, minus 100, minus 105. So this usually is what the PLL is doing, right? Or you will never have a free running VCO which is going to do the upconversion, right? So for now we can ignore this portion, not an issue, right? And here I will just connect it over here. Now here there is a good isolation between RF and LO because these two frequencies are very far apart, right? So that's not an issue. In down conversion, you will put here a what you call a injection filter, right? Because you have to improve the RF LO isolation. So that's what's going to happen. Okay, so over here, what can happen is I can put here a gain stage. So output here is going to be 3.5 gigahertz. So it will be 3.5 E9 plus you are going to have 11 megahertz E6. So the output is going to be, so just one second. Okay, so here there will be a gain stage here, right? And then there will be the image reject filter here. So here let's put a gain stage here. Now in this case it can be a 2-stage or a 3-stage PA, right? So first of all, let me also tell you, so where will it be compressing the output of this mixer? It would be compressing at minus 30 dBm, right? So 1 dB compression is at minus 30. So let's say if I put here a 60 dB gain driver power stage, so we can do a pre-driver power stage. So here a 60 dB, that will result in 1 watt out, right? So let's put here a gain block. Okay, so why does it say this is a power gain block, right? Okay, is there any other gain block here? Just let me see here. This is a variable gain amplifier. Is there an amp here? Yeah, there is a RF amplifier also here. Okay, so we'll come to the distinction later on. So this is more like a voltage gain. So this is a voltage gain amplifier. And this is more like a power gain block. Okay, so let's experiment with this. Okay, I haven't ever made a distinction. So I want a gain of 60, right? So if I put minus 30, is going to give me plus 30, right? Noise figure here is really bad. Let's say 7. Okay, and reverse isolation. So gain is 60. Then this reverse isolation for stability should be around. That's why we split it up. Okay, so instead of putting 1 stage, we can put 2 stages, right? So each one has a gain of 30, for example. Okay, so in this case, the reverse isolation is going to be around 50 or 60. That's a good reverse isolation here. And these are reference frequencies. And what about the compression characteristics? So compression characteristics are not there. So that means that this is just a linear block. Okay, so this is a linear block. Okay, so if I put 30 here, so you'll be coming close to minus 1 dB without any compression, and at 0 it will have a 1 dB compression because this is a linear block. So the first stage can be a linear block. So let's see what's happening here. So I am also doing this for the first time with you, so we will see what happens. And then let's see if amp block has got compression characteristics. So let's see, this is the amp block. Okay, so this looks like a linear, so it says LIN means it's a linear gain, right? And this can be a non-linear block, which is a PA. So this is like a driver and this is like a power amplifier. And let's say the gain is around 30, so the overall gain is 60. Noise figure is around 8 or 7, something like that. Here you see the characteristics. So if I want the compression to be around 30, and then that means that around 34 I'll have the saturation, and then at 12 dB, so 42 will be around the TOI, and then the SOI would be around 54, right? And this is reverse isolation, which is 50 is good enough, and we have 60 dB gain on this. So we are looking at 1 watt output from this transmitter. Okay, so once we are done with this, okay, we have to go here and do something. So for example, let's see if I was to just run this. Okay, what's this? So it says that RF has, okay, output saturation is 24, and on a mixer the Psat is around minus 24, must be greater than output P1 dB by of minus 21. Let's see what has happened here. So P1 dB, oh, so this I did the reverse, sorry, it should be around 24, so that makes sense now, so that would go away. And similarly over here, did I do a mistake here? It says amp1 has been driven past the input saturation point of 4 dBm. Input saturation of 4. Input saturation of 4. The total input power is 7.57 dBm. Input saturation of 4. Okay, let's solve one problem at a time. Psat, the output Psat is much larger than the output P1 dB. Signal source, mixer 1. So Psat minus 30 minus 24 is much larger than the output P1 dB of minus 21. Psat is much larger than the output P1 dB of minus 21. P1 dB here, what is that? Input P1 dB. Oh, so all our numbers are not the output. So basically they are referred to the inputs. So let's make correction here. So this one, minus 30. So this will be happening at minus 40 input. And this will be happening at 24, 34. And then this is input power, referred to input power. This will be 28. And this will be all input power, so I'm just going to subtract 10 out of it. So let's see if that solves it. No. Output Psat minus 24 is much larger than the P1 of minus 31. Okay, it has to be within 5, so it is within 6. That's why it's complaining. It's a warning. So width has to be within that. So at 32, it's not going to complain, is it? It did. Output Psat is much larger than the output P1 dB. Much larger. P1 dB is minus 30. So this is input P1 dB is minus 40. So that means output P1 dB is minus 30. Minus 30, then minus 20, 30, minus 30, minus 28, minus 28, minus 38. So shouldn't it be minus 38? And then 10 above that. So minus 38. And then it will be minus 28, minus 26. And that would be minus 16. So these numbers should be referred to the input side. Okay, so that portion is gone. Then it says RF1 amp has been driven past the input saturation point of 4 dBm. So basically this one is compressing. So this is all referred to output. So see the difference. So for the mixer they were referring all to the input, and for PA they are referring all to the output. So if I put minus 15 here, so just do the maths. If I put here minus 50, then it will be minus 40, and then this will be gain of 30. Minus 40 plus 30 minus 10, right? And ten plus 40 gain. So why would be hitting the saturation? Let's try to understand that. This is compressing at 30 dBm output. Saturation is at 34. So of course it's saying that it is compressing because the input power is at 7. Why the input power is 7? Why would allo be contributing? Because in Gilbert cell mixer, allo, the conversion gain doesn't respond to allo beyond a certain point. Let's put that allo power to be 0 and then simulate this. No valid allo spectrum could be found for the mixer. Oh, so it means that 7 over here is linked here also. Okay, let's see what happens now. Okay, we are back to where we were. The total input power is 1.14 dB. So this is a strange relationship in their equations, right? Allo doesn't affect so much of the conversion gain, but here it does. So it says that it is past the 1 dB compression of 1 dBm, that the input power is 1.14. The current element gain compression at 1.03 dB. So basically just saying that this PA is compressed, right? So for example, if I was to edit this and say I'm going to put here minus 60, then that will not be compressed, right? Okay, and now if I hit a simulate button, so that's not compressed now. Okay, so now having done that, let's look at the spectrum over here. Okay, so let's look at the power spectrum here. So here, this is going to be .115 dBm. The frequency is 3411 here. This is difference and this is sum, and this is the feed through. At 35 there is a feed through which is large, so you do not expect that feed through to be so large. So this is your difference frequency 9, and this is your minus 36, so that's good enough. But this basically is showing up because there is a allo to IF here, allo to IF here. So if I put here 60, because LOIF are, so feed through should go down. So let's look at graph node 2. So you see that LO to IF. So usually you will not see this component a lot. Okay, the feed through components are not going to be so high. So you should get these two components. So right now, this is at 10 dBm out, and this one is at 0. So there is a 10 dB. So that feed through has to be reduced even further. Right, so LO2IF isolation. So if I was to put here an injection, no, that will not have. You have to bring down the LO2IF. So that will be another 10 dB. Okay, and let's look at node 2. So now this sits at minus 20. This sits at plus 10. So this is like a 30 dB. So now this makes sense. Okay, now this is correct. So what this is I hope you understood what that is. Okay, I'm interested in the sum and difference components, right? And this is going to be my output as we discussed over here. If I give an 11 megahertz, it should give me this one and this one, right? So if I put 11 megahertz as one tone, I would get this one and I would get this one. But this component is a feed through, right? So this has to be suppressed. So that I have my baseband look like that, right? So that's what it is. Okay, now looking at the other components. So this is your second harmony, because it is at 7. So this will be spectrum at around second harmonic, which is minus 19, and this is plus 10, so that's around 30 dB below. And this is the spectrum around the third frequency component here, right? And then subsequently you'll have lower and lower. So now you see this is what is desired from a transmitter, right? And then what is going to happen is over here you are going to put that image reject filter which we just designed as a BPF. So if I go here, I can copy this guy, Control C, and I can paste it here, Control V. So we are not spilling anything outside the. So what is the function of image reject filter is we are not picking up noise from around bands other than. So basically this is a input stage. So over here you will have an antenna, and this is the image reject filter, and this is the PA, and this is the driver for that PA. So here the LNA will basically be over here. The input of the LNA will be from node 6 here, right? So this image reject filter is shared along with the antenna between transmit and receive path. So I hope you understood that. So this is a typical transmit chain, the simplified form of a transmit chain, right? And what you have looked at over here, what you have looked at in this graph is that, and this is the noise contribution you can see in this graph. Okay, so this is the noise, and earlier before the filtering you see that the noise level was up everywhere unless you do the filtering. So for example, if this component was not there, right, and then you looked at the analysis. So the function of the image reject filter is the filter, the noise which will fold over in our band of interest wants to avoid that. So if I look at node 2 again here, you see here this noise is flat here, right? So this is your noise level. So if I have this signal over here which is 10 dBm, the noise over here is minus 35. So this is minus 45 dB below the signal, right? But if I put an image reject filter over here, and then run the simulation again and look at this power level, you will see that what the filter is going to do, right? It's going to suppress the noise everywhere other than this band, right? Okay, so that the fold over will not come back here because of the odd order mixing terms. The fold over of this noise will not come in my band. This is still 45, right? Minus 35 here. This is still 45 below. But then if there is a non-linearity in the system, this noise should not fold back over here. So that's the function of this image reject filter here in terms of noise. Of course, when you do heterodyne, you will understand what that image reject filter is doing. So this is a simple system. Now, what kind of analysis can I do here, right? So if I go to system analysis here, and here I go to paths. So here I can specify multiple RF paths along which I want to look at different budget analysis. So I can add a path here. So I am going from multi-source 1 to port number 2. So basically what it means is I'm going from, so let's say that's the path. So I'm going from this source to port 2. Well, there is another RF path which is going to be oscillator to this output port, right? So I can specify multiple paths. So let's say I'm doing analysis on this forward path between the source and the output. So I have added here the path here. So if I go to paths, it says the path goes from multi-source 1 to port 2. Okay, and now if I was to do the analysis, and now if I right click over here, right click over here, I can have more choices here. So let's say if I want to look at gain compression or cascaded gain or gain, right? So if I look at gain, so what's happening over here? Let's see. So this is going to become more interesting. Okay, so I'm doing a gain budgeting. So a mixer gave me a gain. So this represents a mixer. This is my input port here. Okay, so at node 1 I have a 0 dB gain, but at coming to the output node I have 10 dB gain, which is the conversion gain of the mixer. Then from 4 to 5 I have a linear gain, so there is no effect of compression in here, so that will be going from 10 to, so there is a 30 dB gain here which is added. So this is not a cascaded gain, this is per stage gain. So this is a 10 dB gain here, this is a 30 dB gain here, and over here is a 30 dB gain, and then I have a, what would that be? BPF. Okay, because of the frequency upconversion. But this filter is showing what? A rejection. Rejection of what frequency? So, that would confuse you. Okay, what the filter is doing. Actually, filter, we should look at the cascaded gain. The filter should not do anything in that in-band frequency, right? Yeah, so it's a minus 1 dB. Okay, so this is a gain. So don't look at it as a cascaded gain. Look at it as 10 dB here, 30 here, 30 here, and then minus 0.1 here. That's a loss of the filter. Now, more meaningful would be cascaded gain. So if I look at cascaded gain here. Okay, so now what does it say? Let's say this is 0 dB. So gain is 10 here. And then you have a gain of 30. So that becomes an overall gain of 40. Then you have another gain of 30. So that becomes 70. Okay, so that's a 70 dB gain. And then there is a loss of 0.1 on the filter. So cascaded gain will make more sense to you. So I have plus 10, plus 30. So that's 40 here, plus 30, that's 70 here, minus 0.1 from the filter. So you are looking at that. Now, if I was to, so this one is a little confusing. You should see this as compartments. So 10 over here, 30 over here, 30 over here, and minus 0.1 over here. So don't look at this sharp fall off as if it is attenuating. It's just the component level gain. So this one would confuse you. So rather look at the cascaded gain. So in that cascaded gain, you have 10 plus 10 plus 30, that is 40, plus 30, that is 70, then minus 0.01, that is going to be over here is going to be 69.9, right? Now let's see if I expose this to compression. So if I increase the input power, right? So if I add it here, and right now it is going to start compressing at minus 31. Let's see if it is compressing. Okay, say okay and run this again. So here mixer, wow, 0 dB, 2.33 dB is strongly compressed. Hang on. Edit. What happened here? Minus 50. Why is that? So that's wrong. I want to put here minus 50. Right. Say okay. And so I'm boosted the power by 10 dB. So now here the mixer is showing a gain of 9.9. So it is 0.1 dB compressed here. Right. And then linear section will not give you anything. And this PA is also showing a compression. So let's see if there's a compression characteristics here. So let's right click on this node, add a graph. Does it show stage gain, cascaded gain, carrier to noise, channel noise power? Okay, I guess you have to look it in terms of gain compression. So at minus 50, the mixer is 0.1 dB compressed, and the PA, so over here it is 39.9, so this will be 69.9. so this amplifier is 2.2 dB compressed, mixer is 0.1 dB compressed, and the other two blocks will be unaffected. Now let's see if I boost this power further up. Okay, go to minus 45 for example, and run this again and look at this graph. So now the mixer output is 9.6 or 9.7. So in this case it is 0.3 dB compressed, the mixer is 0.3 dB compressed, and this stage will not show you anything. So if this is 9.69, this will be 39.69. So no compression because this is a linear stage. Then 39.69 to 69.69. So 69.69 means what? 69.69, this is 69.2. So it is 69.69 and or 69.7 and 69.2. So in this case it is 0.5 dB compressed. So the PA is 0.5 dB compressed and nothing will show up on the filter, right? So now if I give it minus 45 input, okay, so let me see if I'm recording. Yeah, so if I give minus 45 input, then if I look at the compression, the mixer is compressing by 0.3 dB and the PA is compressing by 0.5 dB. Now if I was to put this, if I was to insert more, so let's see if I put in minus 40 and run this simulation again and look at the cascaded gain. So mixer is 1 dB compressed now. So mixer is showing you a gain of 9 dB, while the under small signal the gain is 10. So mixer is now 1 dB compressed here, right? And then there's nothing over here. So my 9 and 39. From 39 to 67.7. So 39 to 69, I am going, instead of 69, I am getting 67.7. So that means that the PA is compressed by 2.3 dB. Right, so the PA is compressed by 2.3 dB, and then there will be no effect on the BPF. So you understand, we have looked at the compression characteristics, or we have done the linearity budgeting over here, and our system is capable of putting out. So this is the total gain of 67.6, right? And here 67.6 is the overall gain. So if I was to put here input of minus 40, so minus 40 plus 67.6, right? Minus 40, so it is delivering 27 point something, right? So that's what it is doing. So if you look at node 2, you will be seeing it is delivering 27.6. So basically it is compressed by 2.3 dB, right? The entire chain is compressed by 2.3 dB, right? And you can see which all components are compressing here. So if you want to design for a certain compression, you can figure out whether the PA is compressing or whether the mixer is compressing, and then accordingly you can size the transistors of a mixer. If mixer is compressing, you reduce the sizes of the transistors or you increase the current, so that will improve the compression characteristics of the mixer. Now if the PA is compressing, basically then you have to figure out whether it's a driver stage or a power stage compressing. You might need a larger transistor at the output. So I guess you understand how this system view is useful in RF analysis, right? And it will give you component specification. From the performance of the transmitter, you are getting the component specifications, and according to this specification you are going to design the circuit, right, for a given performance. So this is like a top-down approach. You start with the system, you look at all the budgeting over here. So in case of a transmitter, you will not be looking at the noise, but in case of receiver, you will be more focusing on the noise, right? Here you are more focusing on linearity or the gain, right? Or the gain budgeting or the power. While in the receive chain, you are more concerned about the noise figure, right? And of course, you know, SFDR and things like that. So once I discuss that, you will have more insight into receiver side. So here you will see cascaded noise figure here, and this is the stage dynamic range. So what that is spurious free dynamic range. So what is a spurious free dynamic range? Okay, it's a gap between the sensitivity or the minimum signal level to which a component would respond to its TOI on the higher side. That is called the SFDR of a component, right? So that will be making more sense when we do receivers, right? So the budgeting on a transmitter is more of a gain budgeting, power budgeting, or a linearity budgeting, while on a receiver it's more of a gain budgeting and the cascaded noise figure budgeting, because here you are more concerned on a receiver for signal to noise ratio and the sensitivity and the TOI, right? That's there. Now even order mixing is more important for a receiver than the odd order mixing, and we will talk about and this is true in case of heterodyne receivers. Okay, in homodyne receivers you have even as well as odd order mixing important. Both are important, but in a heterodyne, it is on the receiver, it is the even order mixing is more important than the odd order mixing. Odd order mixing is more important for the transmit chain, or because we have discussed that in terms of, you know, interchannel interference or spectral regrowth, right? So we have discussed this spectral regrowth. So linearity is more important on the transmit side when it comes to spectral regrowth, right? Again, this compression characteristics will show up in a constellation also, right? So if I was to talk about a constellation, okay, this entire thing, so if I just say what compression will do, compression will take this and move it in. So the entire thing would basically move in. So now this is rotation. How do I move in? Okay, so these will move in. Sorry. Okay, where did I move it? Anyway, so what I'm saying is these symbols, the corners are going to move in, right? This is going to be the compression characteristics of the transmit chain. So these corners are going to move in, and then this constellation may rotate if there is an IQ imbalance. So this entire thing can rotate, right? So this entire thing can basically rotate. So that's what's going to happen with the IQ imbalance. They're going to rotate. But then what the phase noise is going to do, so if you see here, this one has the phase noise characteristics over here, and maybe later I'll show you what that is going to do. Is that is going to make your constellation dance like this, and this is not statistically predictable because the phase noise is not statistically predictable. So if it dances like this, then the bit error rate would suddenly bump up, or you will have the system compromised completely because the phase noise is not predictable. So if something is deterministic, then you can reverse its effect. But something like phase noise of a PLL, this constellation starts dancing, and if you cannot predict its dancing, you cannot recover your bits. So phase noise becomes very important, and you can see this dancing once I show you with the phase noise what is going to happen. So I am going to stop here, and I hope I got you introduced to Spectrasys, and this is a transmit chain in Spectrasys. Next I'm going to look at the receive chain, right? And then you would have the channel model, right? And channel modeling becomes very important in communication system, right? So accordingly you will have to design these components. So I'm going to stop here. I have taken a lot of time, I think beyond 1 hour. Yeah, thanks a lot. Thank you.